Hello and welcome. Today, we're diving deep into the world of modern mineral exploration, uncovering how experts find valuable deposits hidden beneath the Earth's surface. The secret isn't just one magic tool, but a powerful, strategic integration of three key disciplines: remote sensing, geophysical surveys, and field geochemistry. This combination creates what we call mineral prospectivity mapping, or MPM. It's like creating a treasure map for geologists, using layers of evidence to pinpoint promising targets and guide every decision, from scanning vast regions to planning precise drill holes. This entire process is a smart, sequential journey. We start big and broad, using low-cost methods to cover huge areas, and then gradually narrow our focus, zeroing in on smaller zones with higher confidence. It's all about maximizing efficiency and increasing the odds of a major discovery. So, let's begin our exploration journey with the first phase: reconnaissance and regional targeting. In Phase 1, the goal is simple: identify large, promising regions, known as metallogenic provinces, without breaking the bank. Think of it as the first wide-angle scan of the landscape. Here, remote sensing is our primary tool. Using satellite images at scales like 1 to 50,000 or even 1 to 250,000, we get a bird's-eye view that reveals major geological features. This technology is incredibly powerful for spotting the telltale signs of mineralization from space. We can identify specific alteration minerals like argillic, phyllic, and silicic clays, or minerals like alunite and jarosite, which often form around ore deposits. Remote sensing also highlights important structural data, such as faults, shear zones, and lineaments. These surface clues the alteration zones, the right types of host rocks, and the major structures give us our very first targets. Next, we bring in the geophysical surveys. Airborne methods, like aeromagnetics, are perfect for this stage. A plane flies over the region, quickly and cost-effectively collecting data that penetrates deep below the surface. This helps us map out the broad geological architecture that isn't visible from above. For example, magnetometry maps can reveal features that control gold mineralization, like hidden geological lineaments or intrusive magmatic bodies, which are often buried under layers of soil and vegetation. These surveys give us a foundational, three-dimensional understanding of the subsurface. Finally, we hit the ground with field geochemistry. This isn't about detailed sampling yet. Instead, we conduct broad, low-density surveys. A classic example is stream sediment sampling, where we might collect just one sample every 50 to 200 square kilometers. We analyze these samples for specific target elements and what we call pathfinder elements, other elements that are commonly found alongside the one we are looking for. The results create a chemical fingerprint of the area, revealing geochemical provinces that are enriched in our target. This chemical data serves as the crucial confirmation, validating the potential suggested by the structural and alteration maps we created using remote sensing and geophysics. So, at the end of Phase 1, we've successfully integrated these three data types to dramatically shrink our search area. We've gone from a massive leasehold to a much smaller, more manageable set of prospecting licenses that contain the most promising zones. This sets the stage for a more focused and detailed investigation in the next phase. Now we move into Phase 2, prospecting and target delineation. Having identified our high-priority areas, the mission is now to zoom in and increase our geological confidence. We need to systematically explore the anomalies found during reconnaissance to see if they hold real potential. The first step on the ground is detailed geological mapping. Geologists walk the terrain, mapping at a much finer scale, perhaps 1 to 50,000 or 1 to 25,000. This fieldwork is essential to ground truth our initial interpretations from remote sensing, confirming rock types, structures, and contacts. High-resolution satellite imagery is still in play here, helping us map specific alteration patterns in greater detail. For instance, identifying zones of silicic alteration can highlight the importance of faulted areas in certain types of gold deposits. With our targets narrowed, geophysical surveys also become more focused and intensive. We shift from airborne surveys to ground-based methods, like induced polarization, known as IP, or electromagnetic surveys, known as EM. These are conducted at a much closer spacing to refine the anomalies we detected earlier. Ground geophysics is fantastic for building a three-dimensional model of the subsurface. For example, it can help outline the shape of porphyry copper deposits and detect areas of low resistivity that often indicate the presence of sulfide minerals. We then interpret these new geophysical results, like magnetic anomalies, alongside our detailed geological maps. This allows us to precisely locate and characterize the pollutants and structural controls that are associated with the mineral system. At the same time, our geochemistry work ramps up significantly. We move from low-density stream sampling to high-density soil and rock chip sampling. This is done on closely spaced grids, with survey lines perhaps 100 to 300 meters apart, and samples taken every 10 to 50 meters along those lines. This intensive sampling helps us outline the precise location and extent of the mineralization on the surface. We then take this data and create ISO-grade contour maps, which visually show the distribution of different elements. These maps are invaluable for guiding where we should plan to drill. A geochemical anomaly map, showing high concentrations of gold, becomes a top priority drill target, especially when it lines up perfectly with faults or lineaments identified through our geophysics and remote sensing work. The culmination of all this effort in Phase 2 is a much clearer picture of our target. The combined results allow us to begin estimating mineral resources in what are called the indicated and inferred categories. We are no longer just looking at possibilities. We are building a robust geological model and preparing for the final, definitive step of exploration: drilling. This brings us to Phase 3, the grand finale of our data integration strategy: mineral prospectivity mapping, or MPM. This is where we bring everything together: geochemistry, geology, geophysics, and remote sensing in a sophisticated, multi-criteria decision-making process. Think of it as the ultimate synthesis of all our evidence layers. The first step in creating our MPM is data layer construction. We gather all the datasets we've collected and organize them into a decision matrix, with each dataset forming an indicator layer. Let's imagine a case study for gold mineralization. Here, our integrated dataset might consist of three main criteria. First, geology and remote sensing. This includes our fault maps, our rock type maps, and multiple alteration layers we've extracted from satellite imagery layers for argillic, phyllic, propylitic, silicic, alunite, and jarosite alteration. Each one of these is a clue. Second, geophysics. From our airborne magnetometry, we would use the tilt angle and the reduced to pole, or RTP, maps. These layers highlight key subsurface structures and magnetic bodies. And third, geochemistry. This includes our single-element gold concentration map and a derived gold factor map, both created from our stream sediment data. Once we have all our indicator layers, we need a way to combine them. This leads to the next step: quantification and scoring. To integrate these different types of data, they all need to speak the same language. We classify and score each layer using a powerful statistical tool called the concentration number multifractal model. This method allows us to categorize the data in each layer and assign new scores to each category. It is a way to standardize the information and help compensate for any gaps in our knowledge about the complex mineralization system we are studying. With our layers scored, we move on to weighting and synthesis. Not all evidence is created equal. Some clues are more important than others. To quantify this, we use techniques like the Delphi method. This involves bringing together a group of experts: geologists, geochemists, and geophysicists, and using their collective knowledge and experience to assign weights to each criterion and indicator layer. These weights reflect how important each piece of evidence is for finding our target mineral. The resulting weighted, fractal-based layers are then mathematically synthesized using advanced outranking approaches like Topsis and Viker to produce our final map. The final output is the mineral prospectivity map itself. This map visually identifies the most highly favorable zones for mineralization, highlighting reliable exploration targets and distinguishing them from the less promising surrounding areas. But we don't stop there. We perform a sensitivity analysis, often using what's called the leave one out method, to test how much each criterion influenced the final map. In one study, for example, researchers found that removing the geochemistry criterion had the biggest negative impact on the map's accuracy. This confirmed the absolutely critical role that geochemistry plays in tying all the other indicators together. Ultimately, this strategic integration ensures that the broad-scale information from remote sensing and geophysics, which delineate large structures and alteration zones, is sharpened and validated by the fine-scale details of field geochemistry. This process defines precise, high-confidence targets for the final and most expensive phase of exploration, drilling. It's a powerful, data-driven strategy that transforms the hunt for minerals from a game of chance into a calculated science. Thank you so much for joining me on this deep dive into modern mineral exploration. If you found this journey as fascinating as I do, please hit that like button, subscribe to the channel, and ring the bell so you don't miss our next adventure. See you next time.